Hello, my name is Evan Acosta, and this is my Lab 3 video report on black hole orbits and curving motion. So, the overall goal of the lab was to observe the motion of orbits and curving motion of celestial bodies, and then be able to apply our knowledge of curving motion to manipulate and create a digital simulation in GlowScript. So the first half of the lab was a black hole and a star orbiting around the black hole, and using what we knew about the curving motion, we could find the mass of the black hole. And then in part two, we would see how adding multiple like celestial bodies in the form of a planet and a moon would affect how the curving motion is propagated. And then the lab is basically just to allow me to use what I've learned in class so far to see how it would kind of react in the real world, or at least in a digital simulation, and be able to just manipulate and play around with how the physics actually works. So first, we're going over the fundamental principles that were used during this lab. So the first one is gravitational force, which is the force by two celestial bodies on each other. So like the sun and the moon, Earth and the sun, Earth and Mars, that kind of thing. Um, so this is going to be used to find our parallel and perpendicular forces. And then there's parallel and perpendicular forces, which were equations that are derived from Newton's second law, and they describe the force of an object during curving motion. So as an object curves, it is basically moving in a radius of a kissing circle, and the perpendicular force points in the direction in the center of the kissing circle, and it is basically the force that is changing the direction of the object, allowing it to actually curve. And then the parallel force is changing the speed, so it acts along the curve in the direction of motion. So here are my two simulations. So the first one up here is the black hole part 1, and then the second one down here is part 2, which is the moon, the planet, and the ship. This on the right side, we'll take a closer look at this, but this is just the finding the mass of the black hole over here. So observations, finding the black hole mass was relatively straightforward, as you can see. This is, sorry. Oops. Okay, so I was able to basically just calculate the mass of the black hole here by calculating each component. So you can see I was able to find the change of velocity, change in momentum, and then use that to find the total net force, and then use that to split it up into the perpendicular and parallel forces. And then using that, I was able to kind of create an equation, which I can show you in the slide after this, that allowed me to find the mass of the black hole. And then I just had it loop through and recalculate and print it, which is already in the program. And yeah, basically printed out the mass. For part 2, I used the gravitational force formula to calculate the force of each celestial body on each other. Um, this is this right here. So force of the moon on the ship, force of the planet on the ship, force of the ship on the moon, force of the planet on the moon, just that kind of stuff. And then see how they kind of reacted to each other. Um, so about this shape right here, I saw a cool looking shape on a discussion while I was scrolling to kind of just see how, because I was having trouble working on it. Um, so I wanted to try and get it, so I kind of just plugged in numbers until I got something that looked like it. So I thought the shape was cool, so that's why I put it in. Here are my calculations. This is the formula right here. This last one is the formula that I used to find the mass of the black hole, and then this is just a close-up of some of the calculations that I used to find the mass of the black hole. So what does this all mean? Um, how are the parallel and perpendicular components of force different from the change in momentum and the parallel and perpendicular components of that? So both concepts are basically the same. Like for instance, yeah, the force is equal to the change in momentum. However, you can find them in different ways. For force, if you wanted to find the net force in an object, you have to find all the other forces acting in that object. So it could be a ton of different forces. It could be friction, normal force, gravitational force, some kind of external force. But with momentum, if you are able to find just the final and the initial velocity, and then find the change between those, and then the final time and initial time, find the change between those, then you could find the change in momentum. And that could also help you find the net force. And then last, what if in a system containing the black hole and star from part one and the ship, planet, and moon for part two, so they're all together, um, I think that you would need to see how each body affects the other in order to observe the total motion of the system. But I do think that there would be some dominant interactions. The bodies with the largest mass, like the black hole and the sun, probably would exert more, like a decent amount of like the total force in the system on the smaller objects, like the ship and the moon. But the ship and the moon wouldn't exactly be like pushing and pulling the sun and the black hole. So. And that is pretty much it. I can go ahead and show you guys my program. Here's this. This one is the one that finds the mass. So you can see here. The arrow scale is a little off, so it gets a little big around. Yeah, right there. But yeah, I just did that so that way you could see the arrows when they're over here. And then here is the cool shape that I found on that discussion. So yeah, that's it. Alright, thank you guys for watching.